So we're going on to a unit which involves polynomial functions, and later we'll do something besides polynomial functions. We'll do something called rational functions. But yeah, we want to start in chapter 4, section 1. So chapter 4, section 1 is about polynomial functions. Now I know probably in your past, through Algebra 1 and Algebra 2, and maybe if you ever had our college algebra class, it's kind of like a Algebra 1, Algebra 2 combined with a little tiny bit of pre-calculus, but it's mostly Algebra 1, Algebra 2 from high school. That's what college algebra here is. If you ever taken any of those classes, you would have done a little bit with polynomials, but not really a great deal with the analysis of polynomials, and that's what we want to do. So first of all, we want to define what a polynomial is. So a polynomial of degree n, is a function that may be written in the following form. F of x is the symbol we're using for the function. an x to the n plus an minus 1 x to the n minus 1 plus an minus 2 x to the n minus 2 plus so on and so forth, a2x squared, a1x plus a0. So these numbers, these a numbers out front, so these dudes, I'm going to underline them in blue, these are what are called coefficients. They're coefficients. So they have to be real numbers. Real numbers, anything that can be represented in decimal format. So it could be, they could be whole numbers, they could be negative numbers, they could be fractions, the a's, they could be fractions, they could be decimals, anything that can be representable in a decimal format. And what's really key here is this an, this first an, this one in the front, I'm underlining in red and circling in red. That cannot be 0. That cannot be 0. And this particular one is called the leading coefficient. Leading coefficient. Now the other numbers can all be 0. All the other a's can be 0 if they wanted to. But there has to be at least one of them that's called the leading coefficient that's not 0. Yeah. So, what we want to do some analyzing polynomials. We want to determine their degree, first of all. Remember what the degree was. The degree here is basically the largest power, right? Degree n. Degree n is the largest power. And the leading coefficient is the number in front of the term with the largest power. That's what the leading coefficient is, right? It's the number in front of the term with the largest power. So that's what we want to do. So first of all, we look at our number 1. First of all, tell, is it a polynomial? Yes or no? Is it a polynomial? And then if it is, if so, find its degree and its leading coefficient. Oh, so the first one is going to be a polynomial. So basically, to determine if it's a polynomial, you have to look at these powers here. And are all these powers here? So this one has a power of 1. You don't see that. And this very last one, you can imagine, has a power of 0. Are those whole numbers? Yeah, right? They're all whole numbers. The smallest whole number is 0. But negative numbers are not whole numbers. So 0 is the beginning whole number. And then 0, 1, 2, 3, 4, 5, counting numbers. So yeah, it has all whole numbers. The powers are all whole numbers. Yeah. So it satisfies the form. of a polynomial. So yes, f of x is a polynomial. And it has all these coefficients, right? 3, 4, negative 2, 8, 10. This would be negative 1 right here, 18. And then it has a constant of 21 on the end. That's called the constant term. That's the one with where you don't actually see a variable on the end, but you can construct a variable and call it x to the 0 right there if you wanted to. Okay, now what's the leading coefficient? So the leading coefficient, the degree, right? We want the degree. A, we're going to do the degree. So the degree is the largest power. That's this one right here. So we're going to write deg. Deg is the shorthand for degree. It's the abbreviation for degree in mathematics. The degree is 7. And the leading coefficient, we'll do that in green. That's going to be the coefficient of the largest powered term. Coefficient of the largest powered term. So it's going to be, I'm going to call it the LC for short. Leading coefficient is going to be 3. Okay. So let's do a number 2. We'll write down another function and see if it's a polynomial, yay or nay, and then we'll see, okay, is it, what's its degree and what's its leading coefficient, if it is a polynomial. If it's not, then we just disregard the A and the B part. So is this a polynomial? Well, I mean, you can rewrite this. So we're going to rewrite this in what's called descending order. Descending order, where you go from the largest power to the smallest. So you write minus x to the 4th, and then you have a plus 7. And if you wanted to, I mean, you could put a little, x to the 0 there if you wanted to on that 7, but I'm not going to bother doing that. I'm just going to leave it as a constant plus 7 there. All right, so is this a polynomial? Yeah, this is a polynomial. So you have these positive exponents, whole number exponents, I should say, because this last term is x to the 0 power, so that's a whole number. So it has whole number exponents. Whole number exponents. Oh yeah, this is a polynomial, yes. Okay, now remember what the degree is. Degree it's the largest exponent. So this one here had an exponent of 0, and this one has an exponent of 4. Obviously, the largest exponent is 4. So the degree of this polynomial is 4. So part A is done. Part B asks about the leading coefficient. So you have a coefficient here of -1 in front, and then you have a constant of 7. So the leading coefficient is going to be this -1 here in front of the largest power term. So the leading coefficient here is -1. Okay. Let's do another example. So number 1, number 2 are both polynomials. Number 3, we're going to have x squared minus 2x plus 1 plus 1 over x minus 3 over x squared plus 1 over x cubed. So it looks like we start off with the polynomial. These first 3 terms are polynomial-like, but then these last 3 are not. So, I mean, you could actually rewrite this. You could rewrite this. So we could rewrite this as x squared minus 2x plus 1. Then continue plus, so if you ever had an algebra course, you would know that you can rewrite 1 over x as x to the minus 1 power. And then the minus 3 over x squared, you could write minus 3 over x to the -2. And then 1 over x cubed, you could write as plus x to the minus 3. So basically, when you have those individual variables on bottom, like this one on bottom, this is the same thing as x to the 1 on bottom, you can take that x up top, and it becomes a -1 power. And likewise, when you have this x squared here on bottom, just a single x squared on bottom, you can take that up top, and it becomes a negative power 3 times x to the -2. And then, like this very last one, you have x cubed in the denominator, just an x cubed, nothing else. You can take that up top to the numerator, and it becomes x to the minus 3 power. This is something you would have learned in a more basic algebra course. So we do that in our college algebra course, which is a sort of prereq for this. So hopefully you've seen that. So what do we notice? We look at the powers here. So you have a power of 2, a power of 1. It's understood that you have x to the 0 power on this 1 constant. And then you have these negative powers. So these are not whole number powers. So remember with a polynomial, if you go back and look at the definition of a polynomial, the last thing here, if you look, the last thing here is the constant, where you would have an x to the 0 power. It doesn't allow for having negative powers. You can only have whole number powers. Now that's a key for a polynomial. You only can have whole number powers. So as soon as you have a negative powers, you're no longer in polynomial territory. So what we're going to say here is no f of x is not a polynomial, since there are x variables with negative powers. Yeah. So those ones right now that are circled in yellow, those are the negative powers. Those are what keep this whole entire function from being a polynomial. All right, so number 4. Or another thing you could have said, if you didn't want to rewrite it, you could have looked see where we have this circled in red right here? If I can get that to right. You could say, there are variables here in the denominator. As soon as you have variables in the denominator like that, you're no longer a polynomial. Something else you could have said. All right, number 4. So here's our function. F of x equals 3x squared plus 2x minus the square root of x plus the 4th root of x plus 6. So part of this is polynomial-like. The first 2 terms are polynomial-like, and the last term, the constant, is polynomial-like. But we got these 2 dudes here, the ones with the radicals. If you wanted to rewrite this using just pure exponents rather than those radicals, you could say 3x squared plus 2x, and then minus, so the square root of x would be x to the 1/2 power. It's a fractional power, so you learn about fractional powers in your more elementary algebra classes. We do those in our college algebra class, the fractional power. So fractional powers are the same thing basically as radicals. And then for the 4th root of x, that would be x to the 1/4 power plus 6. So the blue part is all polynomial-like, but then we got these fractional exponents, the ones here in yellow I'm circling. So those are not whole numbers. So to have a polynomial, all your powers of x have to be whole numbers. So this is not going to be a polynomial once again. No. F of x is not a polynomial, since there are powers of x with, how do I want to say this, fractional powers? Fractional powers that are not whole numbers. Fractional powers, not whole numbers. Yeah. So these fractions, 1/2 and 1/4, they're fractions that are not whole numbers. So sometimes you can get fractions that are whole numbers. For example, you can get a fraction like 6/3. That is a fraction, but it reduces to a whole number, to 2. That would be okay. 6/3 would be okay. But the 1/2 and the 1/4, those are fractions that are not whole numbers. Okay? What else? Or another way you could just say that because there are radicals over the variables. Anytime you have radicals over variables, square roots, fourth roots, third roots, any kind of radicals over variables, you're not going to have a polynomial. It's something else you could just say. Because, I mean, if you look at the definition, going back to the original definition here, the form come on, get this to right. Highlighting this, right? That doesn't have anything about radicals in it. Nothing about radicals in it. All right, number 5. Let's say I got 5x squared plus 3x minus 2. And then I got a fraction bar, and underneath I got 2x to the 5th minus 7x to the 4th plus 8x squared minus 1. So it looks like we have a polynomial on the top of the fraction, and we have a polynomial on the bottom of the fraction. But is this a polynomial? No. This is a ratio. This is a ratio of two polynomials. So if you go back to your original definition, you'll notice it doesn't allow for a big old fraction of two different polynomials. It's just one big polynomial that we want. So no, this is not a polynomial. No, f of x is not a polynomial. It is a ratio of two polynomials. And actually, you'll see later in section, I believe, 4.2, we'll start looking at such things that are ratios of two polynomials. And those are going to be called rational functions. Rational functions are when you have a polynomial on top and polynomial bottom. So this is actually a rational function here. We'll study those later. Do one more example, number 6. What if I have f of x equals just a whole number 121, a constant? Is that a polynomial? Well, think about it. You can actually rewrite this as 121, a variable x to the 0 power. And technically, yeah, this satisfies the definition of a polynomial. So you have a variable x. So even though you don't see the variable, you can write it as x to the 0 power. X to the 0 power is just 1, so you got 121 times 1, which is 121. So x to the 0 power has a whole number, right? That's a whole number power. Whole number power. And you have a leading coefficient of 121. So yes, f of x is a polynomial. The leading coefficient is the number in front of the largest power x term. So largest power x term is x to the 0 power. So the leading coefficient is the number in front, 121. And the degree, have we done the degree yet? We got to do the degree first, right? The degree of this dude is 0. It's the largest power. So b would be the leading coefficient, 121. Is that how we were doing it before? Yeah. Degree first and leading coefficient second. Okay, so that's called a constant polynomial. And we know when you graph that one, when you graph a constant polynomial, that's just a horizontal line. We've done that before. Okay, so that's just an introduction to polynomials. How do you know whether something or not is a polynomial? We want to identify those two things. That's going to be important later when we're analyzing polynomials graphs. We want to know the degree and their leading coefficient.